This is Dr. Wood with Citadel Civil Engineering, and this is CIVL202 statics. And in this lecture, we're going to be covering the terms associated with vectors. The first place that I want to remind you of course, is that statics is an important stepping stone, a first in your dialectic stage in your educational journey. And so today is the best day to master these terms from statics. Furthermore, I want you to recognize where we are in statics itself. We're starting on force vectors, and the concepts that we're going to talk about today, we will use through the whole rest of this class and into your classes in future semesters. We're going to use force vectors to be able to talk about force systems and friction and particle equilibrium. All of these topics at some point will have vectors incorporated in them. And so at this point, it is important for you to embrace mastering the concepts that we're going to cover in statics. Now, the first thing we need to do is distinguish between two different types of quantities. The first type of quantity is a scalar quantity. And a scalar quantity is one that can be fully defined in terms of its magnitude alone. Keep in mind, as engineers, we measure quantities in the real world, and so this magnitude is going to have with it a particular unit. And so quantities that have magnitudes might be things like mass, which with its units of kilograms or slugs. Arguably time might be a magnitude where we're not worried about the direction because that's implied, and we just need to know its size. So if we have a scalar quantity and we can describe its size, then we have everything that we would need to know. Now that a scalar quantity differs from a vector quantity. With a vector quantity, magnitude alone won't be enough for us to fully define that quantity. And I can think of no one other than Vector himself who better describes what a vector truly is. And so let's watch this brief clip to learn something from Despicable Me.
I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh, yeah!
Hopefully when you watched the clip, you recognized what magnitude said a vector was. A vector has both magnitude and direction. It's represented by an arrow. So we might have an arrow like this, representing a vector quantity. That vector is going to have a magnitude indicated by some sort of length. And so maybe that vector looks like this, between 2 points. It's also going to have a direction. So that direction piece is going to require a reference line and some angle off that reference line. And so this is how we would talk about a vector quantity. This point up here, B, would be the head of the vector, and A is going to be the tail of the vector. The head's where the arrow is in our mathematical arrow. Your author in your textbook would call this vector, so V for vector, A to B. So keep in mind, when we write symbols like this, mathematical symbols, we're actually doing shorthand, mathematical shorthand. We're writing a sentence. And so this symbol would be read as the vector from A to B. And to know that it's a vector, we would put an arrow over the top. That's what tells us that this is a vector. This is what your textbook's going to do. Your FE reference handbook would refer to this vector using this notation, where again, we're going to have an arrow indicating a vector, V for vector, so this would be the vector B with respect to, that's what the slash, how we'd read the slash, V vector B with respect to A, so B with respect to A. So it's like we're standing on A and we're looking at B. That's what that vector tells us there. And if we wanted to break this down and describe it fully, we would say the vector B with respect to A is going to be equal to the magnitude of B with respect to A. And the way that I know it's a magnitude is that it doesn't have an arrow on the top. Now, in your math classes, you might have put absolute value lines around it to indicate magnitude, but we're actually not going to do that very often in this class. You're welcome to in your notes, but it can get a little cluttered. We're just going to do the magnitude by itself. Keep in mind this is a quantity, so it would have units on it. Maybe this is a position vector, so our units for the magnitude might be length in centimeters, right? So in this case, looking at this is around 40 centimeters there. And then we're going to show it at an angle. So we're going to have that magnitude at, so there's an at symbol like in your email address, at some angle alpha, that's the Greek letter alpha, and then we'll show an arrow and an angle with our, whatever our reference line is. And so in this case, if we were to actually put numbers to this, because y'all all like numbers, we would measure the magnitude as 40 centimeters. And again, engineers always use units. And so we would say here 40 centimeters at, and then how would we measure the angle? Well, we could use something like a giant protractor. Put it in play here. It looks like about 25 degrees there. So at 25 degrees up from our horizontal reference line. And so we see here that with this vector, it has both magnitude and direction. So that's how a vector would be expressed. So we have an arrow, vector, magnitude, and direction. Now, it turns out that vectors can have different relationships with one another, and there's a whole vocabulary about describing these type of vector terms. And so the first thing we might do is introduce a set of vectors. So I've got the vector A here. We see that it has magnitude, 72 centimeters. It has a direction. We could draw that to a number of reference point. There's vector B, vector C, and in each case, they have magnitude and direction. The first term that we might want to talk about is that we would notice that all of these vectors are coplanar. Coplanar. And coplanar means that they're all on the same plane, coplanar. So in this case, they're all within this two-dimensional plane that the board is in. So there's our coplanar vector series system. If it was non-coplanar, one of these vectors might be hanging out in space doing a 3D thing. So non-coplanar would make us in 3D. But for the moment, this is coplanar, 2D. We could take all these vectors and we could adjust their directions so that they all pointed along the same line of action. Well, we'll just do it with 2, okay? And if they were in the, so they have magnitude and they share the same direction, we would call them collinear. Collinear. So they're along the same line, collinear, which actually makes this a one-dimensional system of vectors. So coplanar, collinear. If we're looking at coplanar vectors, our vectors could also be concurrent. And if our vectors are concurrent, they're all going to have lines of action that pass through a common point. So if we modify this just a little bit, and we extend our vectors along their lines of action, like so, we notice that they have a single intercept point, which would make this a concurrent vector system. So lines of action through a common point. That's important enough, we're going to write it down. Lines of action through a common point. Remember, I'm doing PT as my subscript for point, or my abbreviation, through a common point. So that's a concurrent vector system. We could also have a non-concurrent vector system, where if, say, I move B and I put it down here, and I extend its line of action, we'll notice now that there are multiple intercept points, and so we can also have a non-concurrent vector system where the lines of action don't pass through the same point. And this introduces distances between the lines of action. That's going to be very important when we study our force systems in a couple of lectures. So this is how our major terms come into play. In the next video, we'll start talking about vector mathematics because it has its own mathematical art. But for the moment, these are our major terms. So keep in mind, a scalar term has magnitude, a vector has magnitude and direction. I'd love for you to be thinking of some examples of vectors that we might use in our physics classes or in statics. We've already talked about one, position vectors. And then within those vectors, they can be coplanar, 2D, non-coplanar, 3D. They can be collinear, one-dimensional, all in the same line. They can be concurrent, where they all pass through the same point. So we can say that vectors A and C are concurrent, but that vectors A, C, and B are non-concurrent because they have multiple intercept points. And I look forward to seeing you on the next video and or in class. Take care.